Hi. Welcome to the first video for the introductory statistics class. Okay, so just to help you get some orientation here, what I'm looking at, these are the slides that are in Canvas. You'll see that I can click forward and click back, so it looks basically just like a PDF file. And in fact, when you go to Canvas, you'll see that it is a PDF file. Um, so from time to time, I'll drop that off, and I'll just have here be able to do some work on a piece of paper and with a pencil. So you'll see that happen from time to time, but mostly we'll be working with slides. When for each set of slides, there'll be some homework questions to look at, but this is just an introduction. Okay, very good. So let's start in on the introduction. Okay, so usually on a first day, you want to talk about, what is the subject? Is this a subject that you're interested in, kind of thing. So just very briefly, all of these statements on this slide have some statistical content, have some statistical meaning, and most of them are familiar in one form or another. So women make 75 cents to every dollar a man makes is a statistic that you often hear. Average salary of a Major League Baseball player is $30 million. Condoms are 85% effective at preventing pregnancy over the course of a year. If you flip a coin 100 times, there's only about an 8% chance of getting exactly 50 heads. And cigarettes cause about 500,000 US deaths every year. So every one of those is about data. Statistics is about data. So we'll learn in this course about data, about gathering it, about displaying it, about analyzing it, interpreting it, and making decisions based on it. So the whole course is focused around data. I want to talk about the subject of statistics in general just a little bit. So you hear both. You hear people say you can prove anything with statistics. You also hear people say you can't. Statistics can't prove anything. So there's some sort of skepticism out there that statistics is somehow more dubious than, say, nuclear physics. I suppose statistics may be more dubious than nuclear physics, although I'll say nuclear physics uses an awful lot of statistics. But my point is that we will learn the techniques from which you can make reliable, or more reliable than wild guesswork, reliable decisions using statistics. Something that applies especially, sadly, to the times we are living through is that we are under an assault of disinformation. False or misleading information that's spread deliberately with the intent to deceive, and much of that misinformation involves statistical claims. People just say the craziest things. Again, I don't know how to combat that except for a person to, just like at the first bullet point, a person to have a background in sound practice in the field and get some understanding of what is good and be able to tell it from what is bad. I will certainly concede that there are cases where a person says, you got the presidential election wrong there. That's Harry Truman holding up a newspaper that was printed before the result was known that said he lost and when in fact he won. I don't know what to tell you is that if, for example, I'm going to predict, the outcome of a race, and I'm going to say, well, I'm 75% sure that this horse is going to win, then 25% of the time I'll be wrong. That's absolutely true, and we'll talk about that at some length as we move through the semester. I don't know what to tell you. Understanding what can be done and what can't be done is a matter of maturity, is a matter of what are the tools good for, and that's exactly what we're trying to learn. What are the powers and what are the limits of the tools? So, the major point, statistics is about arguments. Just as an example, everybody in the class has a cell phone. When you make a cell phone call, you energize an intentional radiator very close to your brain. Is that a bad idea? So here's some graphic that I downloaded off the web, and it seems pretty endothelial cells and your capillary bed in the brain. It seems a little worrying, I got to tell you. Oops, I'm sorry. For some reason, hit the wrong button. Sorry, apologize about that. So, how to answer the question then? Well, it seems to me that the most reasonable way, the most mature way, the most sound way to hope to answer the question is to provide actual evidence. And when you look at the slide, I click to some evidence, but you can click on that and go to an article on actual evidence. But just as an example, if you take people who are heavy cell phone users for the past decade and you see if they are coming down with these diseases, then you would have some guide. If you have people who are heavy cell phone users, let's say, for example, that for their job they're required to use a cell phone 8 hours a day, and you look at what has happened to them over the past decade, and they don't get the diseases that this scary graphic makes it look like you could get, then you would say, okay, well, graphic artists can make something look bad, but it actually isn't bad. The flip side, of course, is that if you find they are getting these diseases, well, now you have information. So that is to say, statistics is about arguments that are based on more than pictures. Statistics is about arguments that are based on actual information. The two goals of an argument in statistics is, first of all, to find out what's true, and then to convince others that what you know is true. Finding out what's true is hard enough. Convincing others that what you know is true is additionally hard. You can't just go in and say, I've tested a lot of people and I know this to be true. It's more complicated than that. Now, we're not a biology class, we're not a physics class, we're not an economics class, we're not a sociology class. We won't do a lot of the things that you would do if you were, say, a pharmacological chemist. We're not going to cover that. But we will talk about a lot of case number two. What is it that people who do statistical studies for a living worry about when they read a statistical study? Here's a simple example just to try to give a person some idea of what's coming. So here's a doctor of pharmacy, Appalachian State University. When moderate exercise is repeated on a near daily basis. So are you a person who makes it a point to get out every day, every other day, and exercise 40 minutes a day? It says these folks, the study said, these folks have half as many sick days due to colds or sore throats as those who do not exercise. It seems possible, seems perfectly like it could be a true thing. And the person did a study. They collected together a whole bunch of people. Some of them exercise, some of them don't exercise, and we then wait 4 months, and we ask them, have you had a cold in the last 4 months? This kind of thing. So the two questions we will be faced with, the two questions that Dr. Nieman here is faced with, is the claim true, and is the claim proved? Suppose, for example, that you simply went out in the street in downtown Burlington and asked people, are you a regular exerciser? Have you had a cold in the last 4 months? Wouldn't you consider that to be somewhat weak evidence? Suppose instead you had students, you collected students together, you asked them to file a weekly report of how much exercise did you do this week, and also did you get a cold this week? I would consider that, because it's contemporaneous information, more strong an argument. So we will ask, what objections could a fair-minded but skeptical reader raise? Asserting that this person's article, I only have 2 sentences. I didn't do this person a fair trick. But what objections could a fair-minded, willing to be persuaded, but skeptical reader raise, asserting that the report has failed to persuade them? So we will have this person in mind. How can we set up the studies? How can we analyze the studies? How can we present the studies? So that a fair-minded but skeptical person would say, okay, all right, that sounds persuasive. I will often refer to a particular case of a doctor, just trying to have a case that I carry through the semester. So doctor has patients taking a new cold pill. Some of them, the doctor seems to think, complain. Then when the doctor follows up with them, they say, I took that pill, but it gave me headaches. Now, the doctor is not going to go in and do a brain scan on these people. They're just not. So doctor's not going to do a full investigation of the biochemical action of the drug. Instead, what this doctor wants to do is convince other people, doctors, pharmacists, drug chemists, that there's a genuine effect, that this is a genuine side effect of this drug, even though it's not listed in the PDR, the physician's desk reference. So here I am at a Holiday Inn in Kansas City. There's a doctor making a presentation to other doctors, pharmacists, drug chemists, etc. And the doctor is trying to say, this drug has this effect. And if it sounds boring, that's because most things in life are boring. What are the people in the seats thinking? Before the doctor makes that presentation, when the doctor is setting up their study, when the doctor is getting the presentation ready, the doctor needs to be thinking, what are the people in the seats gonna think? So first of all, how can you present the data effectively? First thing, you go to one of those conferences. Talks are 12 minutes long. You have 3 minutes to get to the next talk. 12 minutes is not a lot of time. You got to make your point and make it fast. How can we be sure that the means by which the data was gathered will produce useful data? I gave the example of going on the street in Burlington. That's not likely to produce useful data. If you call up patients and ask, hey, we gave you a new pill last week. Have you gotten any headaches? You're likely to get more yeses than if you simply call up patients and ask, we gave you a new pill last week. Did you have any, we're checking for side effects. And nobody says headache. How big should the study be? The technical sort of mathematical aspects of the study. 5 people is just silly. 500,000 people is too expensive. It's never going to happen. Will 50 people convince people? Will 5,000 people convince the people in the seats? What does it take? Down, as we move from the top of the slide to the bottom, we get to sort of more technical arguments. So suppose you came in and said 12% of people report headaches. Somebody in the seats is going to raise their hand and say, well, maybe it's just the case that 12% of people have headaches. Maybe all you found is the number of people with headaches. That's all. How you know that that's all that different than the number of people walking around the street who have a headache right this moment. Perhaps it's not the pills that cause the headache. For example, maybe there's a new garbage facility in town and people are getting colds, respiratory illnesses, and also headaches. It's for the facility. It's not the pill. And the last one might seem dopey to a person who first encounters statistics, but it's actually the one we'll struggle with the most. Is it possible that this is in some sense a coincidence? That is to say, you gathered this data, you found that walking around people who are not taking the pill were 8% headaches. The people who took the pill were 12% headaches. I don't know. Could it be just that you got a number that's a little high? That's all, nothing exciting? Could that be? How do you refute people who assert that the data is not significant? So somebody raises their hand and says, okay, you came out a little high in the headache numbers, 12 versus 8. But maybe the next study will come out with 6%. That is to say, the study numbers vary. That's the way randomness works. The study numbers vary, and how do you know that 12 is so different than 8 that we should say, well, I'm persuaded? Okay, this is a serious objection that we will spend a long time worrying about engineering answers to. Okay, anyway, so we come down to, having described a little bit what kinds of things we'll talk about through the semester, we come down to a definition of what statistics is. So this course is about arguments. It's about how to understand arguments that others are making, how to evaluate those arguments, and furthermore, how to go on and make arguments yourself. So statistics is a collection of techniques, often based on mathematics, not all of them, often based on mathematics, for using data to support arguments. Data and arguments. That's what it's about. In the course, we'll go through 4 separate steps. Descriptive statistics is the organization and presentation of the data. Design of experiments is principles for the collection of data. Probability, which is actually will be the smallest part of the whole course, is the mathematics of sampling. And finally, the part that we will, in some sense, struggle with the most, the logic of inferential statistics. How do you use samples to infer things about a wider population? That's the part. I don't want to make it sound like this. You'll be sorry you ever meant this. But I do want to make it sound like this is the part that we will sort of spend a lot of time, Chapter 4, Chapter 5, Chapter 6, thinking hard about. Okay, very good. Looking forward to the course. So we'll see you for the next video.